Welcome to This Explainer. Whenever we look up at a massive skyscraper or we're driving over one of those sweeping highway overpasses, it's natural to wonder what is actually holding all of this together. You might immediately think of shiny steel, or maybe that powdery gray cement. But today, we're talking about the true unsung hero of our modern built environment, aggregate. It's basically the perfect puzzle that physically gives our world its shape. And today, we're going to understand exactly how it works.
Okay, let's dive right into this. Here is our roadmap for today. First, unsung heroes of construction. Second, fine versus coarse. Third, the principle of grading. Fourth, establishing size limits. And finally, number 5, the fineness modulus.
All right, kicking things off with Section 1, Unsung Heroes of Construction.
So when you look at the sheer bulk of our buildings, what is actually taking up all that physical space? Well, it's aggregate. By definition, aggregate consists of inert materials that are mixed with a binder, something like cement or lime, to prepare mortar or concrete. Without this essential muscle and bone, the glue of the cement literally wouldn't have anything to hold together. It would just be paste.
And when we compare everyday materials like sand, gravel, and crushed stone to the resulting density of normal weight concrete, the footprint is massive. We're looking at a crucial density of 2,200 to 2,400 kilograms per cubic meter. That is incredibly heavy. It's these everyday, seemingly boring rocks and sands that give our concrete the sheer gravitational weight and strength required to anchor our cities to the earth.
Moving right along to Section 2, fine versus coarse.
And this brilliantly illustrates the contrast. You've got fine aggregates like loose sand right next to coarse aggregates like rugged, crushed stone. Visually, the difference is completely obvious, right? But in engineering, we need a precise mathematical boundary.
So here is that definitive engineering threshold. Fine aggregate is officially classified as being strictly smaller than 4.76 millimeters. Conversely, coarse aggregate is greater than or equal to 4.76 millimeters. That tiny, specific measurement, which actually corresponds to the size of an ASTM number 4 sieve, is the universal magic line between a tiny grain of sand and a structural piece of rock.
Now, before we mix all this together, I do want to give a quick nod to geology, because these materials originate from a magnificent variety of natural sources all over the Earth. We use igneous rocks like granite, basalt, and even volcanic glass. We use sedimentary rocks like sandstone, and we use metamorphic rocks like marble and slate. So honestly, every time you walk on a concrete sidewalk, you are literally walking on an engineered blend of the Earth's deep geological history. How cool is that?
All right, Section 3, the principle of grading.
This brings us to the central puzzle of this whole explainer. How do you strategically mix all these different rocks together to create a perfectly solid, void-free wall? Well, the principle is elegantly simple. The smaller particles fill up the empty pores in between the larger particles. Just picture filling a glass jar with coarse rocks, then pouring in pebbles, and finally adding sand to eliminate all those hidden air gaps. That beautiful, simple logic of pore filling, that is the absolute essence of grading.
Looking at how this is visually represented, from the finest sand on the left, moving through gravel, all the way to coarse crushed stone on the right, you can really see how this particle size distribution comes together to form one cohesive structural whole. It really is a perfect puzzle.
So why do we go through all this meticulous sorting? Well, proper grading is absolutely crucial for 3 massive reasons. Number 1, to secure workability, meaning the wet concrete can actually flow and be shaped by the workers. Number 2, economy in cement use. Listen, cement is the expensive part. By perfectly filling the voids with cheaper rocks and sand, we save a ton of expensive cement, which is economically vital. And number 3, higher density gathered. Less trapped air means denser and significantly stronger concrete.
Which brings us to Section 4, establishing size limits.
So, how are these aggregate sizes physically measured and controlled on a giant industrial scale? Engineers use a series of sieves, basically square wire mesh openings, to determine the percentage of material passing through by mass. Now, don't worry about memorizing these exact numbers, but just grasp the concept here. By shaking the rocks through progressively smaller meshes, from large 37.5 millimeter openings all the way down to microscopic 150 micrometer openings, they get strict control over the exact mix.
But there is a hard physical limit to these puzzle pieces. The maximum aggregate size is secretly dictated by the exact spacing inside the molds they're poured into.
The rocks cannot exceed 1/5 of the narrowest dimension between the structural forms or 3/4 of the clear spacing between the steel rebars inside those forms. Because think about it, if the aggregate is too large, it literally gets stuck on the steel, creating dangerous, empty air pockets right inside your building skeleton. We definitely don't want that.
And finally, Section 5, the fineness modulus.
So here's our final mathematical puzzle. How do we find a single ultimate score for a complex batch of aggregate? We use the fineness modulus. Think of this less as boring math and more as a high-stakes recipe used to definitively quantify a batch's coarseness. Step 1, you sum up the cumulative percentages by mass retained on a specified series of sieves. And Step 2, divide that total sum by 100.
Now, what's really interesting here is watching how this math stacks up in a real-world example. As the sieve sizes get progressively smaller, more and more material gets caught. If we sum up these cumulative retained fractions, 1.82 plus 13.63 plus 31.82 all the way down to 100, it gets us precisely to a total sum of 290.9.
So, following our formula, dividing 290.9 by 100 gives us exactly 2.91. Boom! That single powerful number allows an engineer to instantly understand the average size and characteristics of literally tons of material. It's the ultimate mathematical shorthand for our structural puzzle.
We have seen just how meticulously we have to select, sort, and calculate these inert rocks to successfully build our modern world. But I want to leave you with one final, slightly provocative thought. What happens when the rocks inside our concrete don't get along? Because as it turns out, they aren't always completely inert. Sometimes engineers actually have to mandate the replacement of reactive aggregate with crushed limestone just to prevent invisible chemical reactions that can literally expand and crack the concrete from the inside out. Crazy, right? It really makes you look at the sidewalk beneath your feet differently, wondering what microscopic chemistry is happening down there right now. Keep asking questions, keep exploring, and thank you so much for joining me to figure out the puzzle of aggregate.